So what we're going over today is the last thing, okay, in the physics unit, which is efficiency. Okay? What's efficiency all about? Efficiency is really just a percentage that tells us how much of the energy we put into something actually gets converted into what we want. All right? Obviously, in our kind of day and age here, we're very concerned with efficiency. We want to use energy as best we can and not have waste. All right? And when you look at how kind of everyday objects now operate versus how they operated 20 or even 30 years ago, we're way more efficient now. Prime example, in your house, okay, you probably do not have old style Thomas Edison incandescent light bulbs. Okay? Some people still do, but it's not all that common anymore. Okay? To have those ones that actually have the filament inside, okay, that glows, those are wonderful. They put out light, but they are incredibly inefficient. You turn one of those on, and within about 15 seconds, you can't touch the thing because it's too hot. Okay? Because an incandescent light bulb makes light from heat. Okay? That's what incandescent means. It means it gets so hot that it glows. All right? The little filament, the tungsten filament that goes through the middle, okay? It gets so hot that it glows white hot and puts off a whole bunch of light, but it also puts off a whole bunch of heat. Okay? It is not very efficient. A 60-watt light bulb uses 60 watts worth of power. That means 60 joules every second in order to make light. That's how much a 60-watt incandescent bulb uses. That's what watts are, a joule per second. Okay? So it uses 60 joules of energy every second in order to put out light. How much light does it actually put out? Not much. Most of the 60 joules is heat. Okay? That's not an efficient way to light your house. So about 10 or 12 years ago, we started replacing them with the compact fluorescent ones. So they're like a fluorescent tube, except they're coiled up so that they fit in a light fixture that's designed for a regular incandescent bulb. Okay? Those are quite a bit more efficient. You can replace a 60-watt incandescent light bulb with a 13-watt compact fluorescent. They put out the same amount of light, but one uses 13 joules every second versus 60, because a compact fluorescent light doesn't put out as much heat. All right? It's the gases inside that glow instead, and so as a result, okay, we get the consumption of less energy. Now, we discovered there are problems with these kinds of bulbs. Okay? They're breakable. Okay? I had 2 in my house that caught fire. Okay? And they have lead in them. Sorry, not lead, sorry, they have mercury in them. Okay, which is very bad for the environment, and people were throwing them out like they were incandescent bulbs. Okay, and so as a result, a lot of mercury leached into groundwater and soil and stuff like that. So we found that while they're very efficient, there's a trade-off. Okay, the other thing is incandescent light bulbs last about 1,000 hours. Okay, a compact fluorescent light bulb can last 5,000 to 8,000 hours. Okay, now since we've discovered that there are problems with these, we've gone to LEDs. Okay? You can replace a 60-watt incandescent 13-watt compact fluorescent with a 6 or 8-watt LED bulb. Okay? They're expensive, but they last 20,000 hours. Okay? And they use way less energy. People always look at that, they're like, yeah, but I can buy an incandescent bulb for 25 cents. Yes, but you're going to pay for it. Not the bulb, but you're going to pay for it in energy. Okay? When I first discovered compact fluorescent bulbs about 10 years ago, I replaced every bulb in my house, and my monthly power bill went down 25%. Okay? It's huge. Okay? I mean, the other things in my house still consuming energy were still consuming energy, refrigerator, you know, stuff like that. You know, but the amount of energy being wasted by my light bulbs was considerable. Okay? You change to the more efficient stuff, and you're going to save money. Sure, these bulbs cost 4 times as much to buy outright, but they're going to last 10 times as long, and they're going to save you energy. So it's an investment, right? And LED bulbs, yeah, they're expensive. It's like $10 a bulb, okay? But they're going to last 20 times as long, and they're going to use 1/10 the energy, okay? So you save money in the long run. Everybody follow me there? All right, so that's one example, okay? Now, other example. Or let's actually, I'll ask you this question. If you were, let's say, going to the doctor, would you go to a doctor who was only right 10% of the time? Right? We all go, hell no. I wouldn't go to the doctor who's only right 10% of the time. I go in there, with a headache, and he'd tell me I need my appendix taken out. Okay, that's not going to work, right? That's not going to be effective. So I wouldn't do that. Okay, but we accept horrible levels of efficiency, like around 10%, all the time. Okay, a prime example would be the car you came to school in, or bus that you came to school in, however you got to school. Okay, you probably did not come in an electric vehicle, right? Maybe you came in a hybrid vehicle, but you probably did not come in an electric vehicle, which means you used an internal combustion engine to get here, right? In an internal combustion engine, we turn the potential energy, chemical potential energy in our fuel, into heat, which then causes gases to expand and pushes on the pistons within the engine. Okay? That's what makes the mechanical energy. So we go from chemical to heat to mechanical. Heat to mechanical is the most inefficient energy conversion there is. Okay? But we use it in order to power vehicles. When you do that, 33% of the energy in your fuel goes right out the exhaust system as heat. So if you put $100 worth of gas in your truck, $33 of it is going right out the tailpipe and doing nothing effective. Okay? Yeah, it's not going to, even if you cover up the end of the muffler, it's still not going to make the energy do any work. It's just going to kill your car. Okay? The cooling and heating system. Okay? Listening here, guys. This is how bad your car is in terms of efficiency. Your car is so inefficient and produces so much useless heat that it has to use 1/3 of the energy in your fuel to keep from melting down. You don't. That's the design flaw of the internal combustion engine. And I love the internal combustion engine, but it's a design flaw. Okay? What happens is, in your car, when that fuel is being detonated and burned inside of there, heat gets produced. Well, if you just let that heat build up, the metal parts of the car will melt, and then the car will destroy itself. Okay? So what happens is, your car circulates coolant through the engine block. All right, the green stuff that you might see, hopefully not leaking out of your car. Okay, but that's the antifreeze. That's the coolant that keeps your car from getting too hot. So it circulates through the engine block. In order to circulate it, there has to be a pump. The pump is directly connected to the mechanical parts of your engine and uses 1/3 of the energy in your fuel to run. Okay, so 1/3 of the energy gained from the fuel in your car is being used to keep it from destroying itself. Okay, so now, we've burned $66 worth of fuel, and we have not moved. This is just to keep the car from blowing up. Okay, 66 out of $100. Okay, now, the drivetrain, that would be all the kind of moving parts. Okay, transmission, drive shafts, okay, things like that. Okay, there's a lot of movement in there, and anytime you have pieces of metal connected to each other and spinning, there's friction, and friction generates heat, and that loses energy. 10%. We're up to $76. Okay, we haven't gone anywhere yet. Okay, accessories. That would be windshield wipers, air conditioner, power windows and door locks, touch screen, media center, stereo, rear window defroster, okay, all that kind of stuff. Those are all accessories, your headlights, okay, things like that. Okay, they run off of your alternator. Anything that's electrical runs off of a little generator that is attached by the same thing as your water pump, the thing that keeps the coolant running. Okay, it is also attached to the alternator. It spins and generates electricity, which charges your battery and runs all your electrical stuff. Okay, that uses about 4% of the energy in your fuel. More if you've got one of those stereos that you can hear from a mile away. Okay, so if you've got like 4 amps, 8 subs, right? Okay, I had a kid that I taught back in Lloydminster when I taught there. He had to have an extra alternator installed to power all of his stereo equipment in his like $1,200 1984 Fox body Mustang. Okay, Yeah. Well, here's the funny thing. We had a car show every spring in Lloyd that the kids could bring their cars to and show stuff. And in his thing was the Looney Dance. He would turn the stereo up as loud as it could go, and he would flick a loony onto the top of the Mustang. Okay? And the loony would bounce on the top of the car, sometimes 1.5 feet off the top of the car. The car would vibrate so much. Okay? It was pretty cool to watch. Deafening, but cool to watch. Okay? Well, he was trying to get it to go as high as he, like higher than he was trying to break his own personal record for how high this loony could get. So he turns the stereo like even higher. And all of a sudden, the hatchback window shatters. Okay? Shatters the back window of the Mustang. Okay? And that was, by the way, what he called it, the Mustang, because it was an awful piece of junk. But the stereo in it was worth more than the car was worth by a factor of about 8 or 9. Like 9, one $1,200 car, he had $10,000 worth of stereo equipment in. Okay, so anyway, he shatters the back window because of all the sound waves hitting it were so big that the vibration actually caused it to shatter. Okay, so he actually was probably more on the lines of about 6 to 8% of the energy in his fuel being used because he had to have a separate generator, 2 alternators to run all of the stuff on his car. Because if he didn't have that second alternator, the battery would die. Okay, car could be running, but it would drain the battery because the car couldn't generate enough electricity. Okay? Yeah, it's pretty crazy. Okay, internal friction. Right? You've always got internal friction. This number is probably a little smaller now. We use synthetic oils, which are better, and so they're more efficient. Okay, but that's another 6%. So what ends up happening is, okay, an average passenger car runs at about 14 to maybe nowadays 20% efficiency. Right? And we accept that every single day when we get in and turn the key. They may go 600 kilometers on a tank, but my truck will go over 1,000 kilometers on a tank. It just has a giant tank. Sometimes it's just about how big your tank is. Okay, so yeah, we're not running very efficient vehicles. There's just, I mean, we've done lots of stuff in the last 10 years that have made cars way more efficient. This number is old. Okay, internal combustion engine cars now probably run closer to 20%. Okay, they're good. They're much better than they used to be. Okay, if you went back 50 years, you'd have cars that were running at like 8% efficiency. Okay, they were ridiculous because they were big and heavy, and they all had big V8 engines and stuff. Electric cars, electric engines are way more efficient than internal combustion because they don't generate heat. They turn electricity directly into mechanical energy. There's a small amount of heat produced by that, but an electric engine runs at like between 80 and 90% efficiency. The problem is that we don't have batteries that are capable of really sustaining power for as long as, like, if you're driving along in your car and you start to get low on gas, you pull over, you fill up with gas, you keep going, right? You're out for 5 minutes and you're back on the road. If you have an electric car and the gauge says you're out of power, you pull over, and even the fastest charging stations, I think, are now about like half an hour. Okay, they've got some in California for the Teslas, right? You plug them in. Do they? But it's not like going to the gas station and filling your tank up. It's a lot longer wait. Okay. Now, is an electric car more efficient? Yes. I'm not going to argue that. Okay. An electric car is more efficient. But here's the problem with what people think about electric cars. A lot of people buy an electric car so that they can look at you down their nose and say, I'm saving the planet because I'm driving an electric car. Okay. No, it's not even about that. But here's what that person doesn't understand. Where do we get all of our electricity from in Alberta? Coal. Okay? Like, if you want to save the planet, good for you. I think that's wonderful. But in Alberta, buying an electric car does not reduce your carbon footprint. All it does is make the power plant work harder by burning more coal and putting more carbon dioxide into the air. Okay? The energy required to take you from home to work is the same no matter what kind of car you're driving. Okay? It's a matter of mass and energy you have to get from A to B. Okay? And where you get your energy from is something you need to consider. Now, if you've got a whole backyard full of solar panels and you're going to hook your car up to that and charge it every night, good luck with that because they don't work at night. Okay? Yes, okay, then you're reducing your carbon footprint a little bit, but you have to consider, where does my electricity come from when you buy an electric car? If you want to save the planet, do it. That's great, but make sure you're actually doing it. Okay? Now, what about a hybrid car? Anybody have a hybrid car? I don't have a hybrid car. No. No. That's right. I drive a big heavy truck. I'm part of the problem. Yeah. Okay. So a hybrid car is a good idea. It uses less fuel because it has both an internal combustion engine and an electric engine. Right? Actually, no, the price of them is coming down. They're getting a lot better. Again, there's the issue with battery, okay, with charging power and things like that. But a lot of people buy a hybrid car and don't realize that there's situations where hybrid cars are very useful and they will be more efficient, and there are situations where they're not going to be more efficient. And that is if you drive all highway. Okay? A hybrid car is designed to be more efficient by using the electric engine to assist the gas engine. Right? So if you're stopped at a stoplight and you press down on the gas pedal to accelerate away, the electric engine kicks in along with the gas engine. They work together, and then your gas engine doesn't work as hard. You don't need as big of a gas engine because you have electric assist. Okay? If you drive on the highway, the only time the electric engine kicks in is when you're going up a hill. The rest of the time you run on the gas engine. Okay? The electric engine is there to assist during times of heavy draw or heavy acceleration. So if you're driving all highway, a hybrid car isn't really saving you much because it's not going to be using the electric motor very much. Okay? It's designed to be used in stop-and-go traffic. Then the electric engine in some hybrid cars, or sorry, the gas engine turns off. If you're stopped, the gas engine turns off. And then when you press the gas pedal, the gas engine fires up and the electric engine go together and they accelerate you up to speed. Once you get up to speed, the electric engine turns off. The gas engine runs and recharges the battery that the electric engine draws from. Okay? Well, that's what a hybrid car does. Well, I think actually in some of the newer ones you can. But I mean, again, the issue is that when you run out of electricity, you've got to have gas, or you're cooked, right? But right? Now, I mean, a lot of people, they didn't want electric engines for the longest time because, well, electric engines are dumb and they're slow and whatever. But if you actually, I don't know if anyone saw this, but they had on Motor Trend a few months ago, they raced a Dodge Hellcat. Okay, 707 horsepower. It's everything that's wrong with with saving the world. Okay, big V8 supercharger, uses fuel like it's like it's water. Okay, and they put it against a Tesla, and the Tesla kicked its butt. Okay, the electric car was way faster. Okay, than the gas-powered monstrosity that sounded way cooler and looked way cooler, but okay, was faster. Right, so that idea of I don't want an electric car because it's weak and wimpy is actually kind of gone out the window. Yep. Well, I mean, the gas engine still charges. There's an alternator. Yes, you don't necessarily have to plug it in. You can. There are plug-in hybrids you can plug in, but yeah, lots of times you don't need to. The gas engine will charge the battery. Okay, now listen in here, guys. Okay. The other thing that you do need to consider, it's something you need to consider when you're buying either an electric vehicle or a hybrid vehicle, is the batteries. Okay. Batteries tend to have really harmful chemicals in them. Okay, and they have to be disposed of somewhere. So while you might be reducing your carbon footprint, there's still a chemical footprint involved from the batteries. And there's a chemical footprint involved in an internal combustion engine too. Okay, when you throw an internal combustion engine car away, it's full of oil, it's full of antifreeze. Those are harmful chemicals as well. Okay. But a battery is also full of really harmful chemicals, so it's something else to consider, right? You want to make an informed choice. I'm not trying to discourage you from saving the planet, okay? But it's you want to make sure you're actually doing it, right? Okay, so here's our problem. Cars are not very efficient. They're getting better, but they're not very efficient. Anytime you have one form of energy being converted to another, energy is going to be lost. No energy conversion is 100% efficient. Okay, we talked about that before. That's why a perpetual motion machine can't exist. Okay, no conversion of energy is 100% efficient. And the more energy conversions you have between the initial source of energy and the final work reduces your efficiency. The more conversions you have, the more energy you're going to lose as you go along. Does that make sense, everybody? Okay. So systems with moving parts always lose energy as heat because there's always friction. Okay. That's consistent with what we just talked about, the first and second law of thermodynamics. Okay. Energy, energy can't be created and it can't be destroyed. It's got to go somewhere. But heat always flows from hot to cold. Okay. So when you eat food, your body digests it, converts it to other forms. Your cells can convert that chemical energy to mechanical energy and allow you to move. Right? Is it terribly efficient? Actually, no. Right? When you start working out, do you get hot? Yeah, it's absolute evidence that you've got inefficiency in how we convert things. Because in the end, your body's doing the same thing your car is doing. It's burning fuel. It's just not setting it on fire. Okay? But it's burning fuel. It's converting heat to mechanical energy. Okay. So I guess essentially here what we need to know is you're never going to get close to getting all the energy out of whatever your initial source is. Yeah. All right. Calculating efficiency. Calculating efficiency is pretty straightforward. All right. All you're ever going to do is calculate a percentage. Okay. Efficiency is always measured as a percentage. I'm going to eliminate this times 100 part because we can all do that in our head. Right? When you do when you find a percentage mark on a test or something, right? You take what you got, let's say you got 80, okay, out of 100 marks. Well, when you punch that into the calculator, you get 0.80, right? And you just do in your head, oh, I got 80%, right? We don't have to have that times 100 in there. We know to do that. Everyone okay with that? Okay. So in order to get this number, what we're doing is we're taking the actual work that gets done and dividing it by the amount of energy that had to be put in order to accomplish that. Okay, so the amount of work that actually got done divided by the total amount of energy required to do it. That gives us the percentage of the energy that actually ended up doing what we call useful work. Okay, useful work output. Okay, that's the top number. The bottom number is the work input or the energy inputs. Okay, how can you tell the difference when you're reading a question? How will you know which one's which if they don't use useful work or energy input or whatever? How will you know which one's which? This one will always be smaller. Okay? Now, if you're only given one of them and given the percentage, then you'll have to figure out which one you're looking for. Okay? And that's when it'll say, calculate the useful work output. Well, that means how much work actually got done. Okay? Or calculate the amount of work input. Well, input means how much did I have to put in. So always be looking for output, input, okay, or useful work. Okay? Things like that. Okay. So some examples here. Okay, we already talked about the internal combustion engine. Okay, anywhere, let's say probably now it's more like 15 to 20%. Okay, electric engines can be up to 95% efficient. Steam reciprocal engine, 50 to 75%. Okay, steam turbines, 40%. No, it would be its own type of question. Yeah, in the AP course, I do sometimes do that, but not in the regular. Okay, so let's look at an example here. So I've got a crane that lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work or mechanical energy input. Okay. While doing 8.0 times 10 to the 3 joules of useful work. All right, so which one's my energy input? Which number? The first one, okay? Because it says work or mechanical energy input, so it's the input energy. Plus, I have two numbers here, and this one is bigger. Okay. Okay, and that means that my useful work ended up being 8,000 joules, or 8.0 times 10 to the 3. Okay, everybody follow me so far? If I'm trying to find the percent efficiency of the crane, well, percent efficiency is 8,000, my energy input, divided by the amount of energy I had to put in. 23,000 joules. That's 2.3 times 10 to the 4, right? Okay, so we'll have our 8,000 divided by 23,000. All right, so the crane is operating at 35%, roughly, because I think we only have, or no, we have 3 significant figures there, so 34.8%. Okay, is that a terribly difficult calculation? No, it's nothing compared to some of the stuff you've done in here. Okay, after law of conservation of energy, that should seem like nothing. Okay, I want you guys to try these ones here. I've got the answers on there. Okay, I'll give you guys a few minutes, and then we'll go through like 1 through 3 here. Yes. That'll do it. Okay, so we got an internal combustion engine that's running at 15% efficiency. The first thing I need to do is write down my givens, and whenever I see efficiency, turn that back into the decimal, 0.15. Right? Remember, the efficiency is a percentage. We're taking that multiplied by 100 part out because we can do that in our head. Okay? It's used to do 3.20 times 10 to the 4 joules of useful work. Now remember, efficiency is the useful work divided by the input energy. So, which one did they just give me there? They gave me efficiency and top number or bottom number? Top number. Okay, so our work there, useful work, is 32,000 joules. Okay, that's what 3.2 times 10 to the 4 is. So I'm looking for how much energy did I really have to put in terms of fuel into this object. All right, so I'm going to take my formula and manipulate it by multiplying both sides by EI, and then doing what with EF, or efficiency here. Then I divide it over to this side. All right, so my input energy equals the work divided by my efficiency, which should make sense. If I divide by a decimal, do I get a bigger number? Yeah. Okay, so we'll have here then our 32,000 joules divided by 0.15, and that should give us our 213,000, although we only have 3 significant figures here, so it would be 2.13 times 10 to the 6. Sorry, 10 to the 5 joules. Okay, everybody follow what I did there? Haley, you're squinting at it. What? Yes. So that's why it's 10 to the 5, right? 1, 2, 3, 4, 5. Questions on number 1? How many people have done number 2? Okay, do we need to go over that one? So in lifting a car, the total mechanical energy input of the hoist is 5.61 times 10 to the 4. The useful mechanical energy output is 1.96 times 10 to the 4. This is the smaller number, so it's the top number. This is the bottom number. We're calculating the percent efficiency. So efficiency equals, okay, our work or output divided by our input. So that's going to be 1.96 times 10 to the 4 divided by 5.61 times 10 to the 4. Okay, and when we do that, we should get 34. Actually, we would only get 34.9 here because we have only 3 significant figures. Okay. All right. Keep going. I'll try 3, 4, and 5 there. So for number 3 here, we've got the efficiency given to us. Okay, so we can write that down as a given. Efficiency is going to be 0.85. Okay, in lifting a small load, it produces 15 joules of mechanical energy input. So that's going to be our bottom number. Okay, 15 joules. Right, we're looking for how much useful mechanical energy output does it give us. All right, so efficiency is useful work divided by the energy in. I want to get useful work by itself, so I multiply both sides by the energy in. That should give me a smaller number. If I multiply 15 joules by 0.85, work will be smaller than 15 joules. okay, which it should be because it can't do more work than it got energy, or it breaks the first law of thermodynamics. Okay, so we take our EI, 15 joules, multiply that by 0.85, and we should get 12.75 joules of useful work. Okay. All right, how are we doing on number 4? We need to go over number 4, or just need more time on number 4? More time? Okay. All right, so on number 4, okay, it says in heating a pot of water, 2,000 joules of energy was supplied by the stove element. Okay, if only 500 joules of heat was actually gained by the water, okay, what was the percent efficiency? All right, the bigger number goes on the bottom. Okay, this is how much energy I put in, but this is how much was actually gained by the water. Because it's 2,000. Right? 10 to the 3, this is 10 to the 2. Yep. Yep. Okay, so it's just it's going to be 500, okay, divided by 2,000, which is exactly 25%. Okay? All right, how are we doing on number 5? Okay? Is it pretty much the same question? Yes, it is. Okay. All right, so try 6 and 7 there. I don't know if you'll get to 8 or not, but try 6 and 7.